40 light-years away, a planet exists that should be impossible. Its discovery was barely noticed. Most scientists ignore it. But recent observations reveal something that changes everything we thought we knew about alien worlds and the search for life beyond Earth. LHS 1140b orbits a small red dwarf star in the constellation Cetus. When astronomers first detected it in 2017, the data seemed straightforward. Another rocky planet in the habitable zone. Another entry in the catalog. Nothing particularly special. Except every assumption we made about this world was wrong. Completely, fundamentally wrong. Here's what makes this so strange. LHS 1140b is massive, roughly 1.7 times the size of Earth with about 5.6 times our planet's mass. That density suggests a world made mainly of rock and iron, similar to our own. But the conditions on its surface, those defy every model we've built. The star it orbits is tiny, only 1/5 the size of our Sun, cooler, dimmer, and far less violent. This creates an environment unlike anything in our solar system. Most exoplanet discoveries generate brief excitement before fading into the background noise of thousands of confirmed worlds. We found hot Jupiters that orbit their stars in days. We've detected super-Earths with crushing gravity. We've even identified planets orbiting multiple suns. But LHS 1140b keeps revealing layers of complexity that shouldn't exist together on a single world. The more we look, the stranger it becomes. Think about what it takes to sustain liquid water on a planetary surface. You need the right temperature range, obviously. But you also need atmospheric pressure, magnetic protection from stellar radiation, a stable orbit that doesn't swing between extreme heat and cold, geological activity to recycle carbon and regulate climate over billions of years. Earth has all of these factors working in perfect harmony. The odds of another world possessing the same combination seemed astronomically small. Past tense. Seemed. Recent spectroscopic analysis suggests LHS 1140b might actually have an atmosphere. Not the thin, stripped remnant we expected, but something substantial. Something with molecular signatures that indicates complex chemistry. The James Webb Space Telescope turned its instruments toward this distant world, and what came back was data that made researchers double-check their equipment. Triple checks. The signals were there. Persistent. Undeniable. Red dwarf stars have a reputation problem in astrobiology. They're the most common type of star in our galaxy, making up roughly 70% of all stellar objects. They burn slowly, living for trillions of years compared to our Sun's mere 10 billion. That longevity should make them ideal for life to develop and evolve. Except red dwarfs are violent, especially when they're young. They unleash powerful flares that strip away planetary atmospheres. They bathe their nearby planets in harsh ultraviolet and X-ray radiation. They create tidal locking, where one side of a planet perpetually faces the star while the other remains in eternal darkness. Every one of these factors should make LHS 1140 be a barren, airless rock. Tidal forces should have stripped away any atmosphere within the first few 100 million years. Stellar flares should have sterilized the surface. The planet should be dead. A frozen wasteland on one hemisphere, a radiation-blasted desert on the other. That's what our models predicted. That's what every comparable system we've studied has shown us. But LHS 1140b refuses to follow the script. The planet orbits its star every 24.7 days, locked in that predicted tidal embrace. One hemisphere always faces the dim red glow of LHS 1140, while the other stares into the void. Surface temperatures should vary by hundreds of degrees between these two sides. Yet something is redistributing heat. Something is stabilizing the climate. Atmospheric circulation could explain it, but that requires a thick atmosphere with efficient convection currents. The kind of atmosphere that shouldn't survive around a red dwarf. Scientists initially classified LHS 1140b as a mini-Neptune, a world with a thick hydrogen and helium envelope surrounding a rocky core. This classification makes sense given the planet's mass and radius. Mini-Neptunes are common throughout the galaxy. We've found hundreds of them. They're well understood, predictable, and thoroughly inhospitable to life as we know it. Hydrogen atmospheres create runaway greenhouse effects. Surface pressures reach crushing extremes. Nothing survives there. Then the data got weird. Refined measurements of the planet's density revealed numbers that didn't match the mini-Neptune profile. The world was too dense, too compact. Something about its composition was different. Researchers run the calculations again. They checked for measurement errors. They considered alternative explanations. Each analysis points toward the same conclusion. This wasn't a mini-Neptune at all. This was something else entirely. The current leading hypothesis suggests LHS 1140b might be a water world. Not a planet with oceans like Earth, but a world where water makes up a significant fraction of its total mass. Imagine a rocky core surrounded by a global ocean hundreds of kilometers deep, covered by an atmosphere of water vapor and other gases. The pressure at the bottom of such an ocean would be immense, potentially creating exotic forms of ice despite temperatures well above freezing. The chemistry occurring in those depths could be unlike anything we've observed. Water worlds present unique possibilities for habitability. The deep oceans would shield any potential life from harmful surface radiation. Hydrothermal vents on the ocean floor could provide energy and nutrients, similar to the ecosystems we've discovered in Earth's deepest trenches. The sheer volume of liquid water will create millions of ecological niches. But there's a problem. A massive problem that researchers are still trying to solve. How does a water world form around a red dwarf? Where does all that water come from? And more importantly, how does it survive? Planets form from the protoplanetary disk of gas and dust surrounding young stars. Close to the star, temperatures are too high for water ice to exist. Water only condenses further out, beyond what we call the frost line. Planets that form inside this boundary are typically rocky and dry. Planets that form beyond it can accumulate massive amounts of ice and volatiles. Earth likely got its water from comets and asteroids that formed beyond the frost line and later crashed into our planet. But Earth's oceans are relatively shallow, covering only 70% of the surface to an average depth of about 3.7 kilometers. That's barely a film of moisture compared to what we're seeing on LHS 1140b. For LHS 1140b to be a true water world, it would need to have formed much farther from its star and then migrated inward. Planetary migration is common, driven by gravitational interactions with other bodies in the system and friction with the remaining gas disk. But migration is violent. It heats planets through tidal forces. It exposes them to increased stellar radiation. Most planets lose their volatiles during this process, arriving at their final orbit stripped and desiccated. Yet LHS 1140b somewhat retains its water, somehow protected its atmosphere, somehow survived intact. The numbers tell a story that shouldn't be possible. Current models estimate that water could make up anywhere from 10 to 20% of the planet's total mass. For comparison, water makes up less than 0.1% of Earth's mass. We're talking about a world with thousands of times more water than our entire planet, compressed into a volume only slightly larger. The implications are staggering. But here's where it gets truly interesting. Recent observations suggest the atmosphere might contain nitrogen and possible oxygen. Those two gases together create a very specific signature, one that's remarkably similar to Earth's atmosphere before life filling it with oxygen. Finding nitrogen is significant because it's relatively inert, meaning it doesn't easily react with other elements or get stripped away by stellar wind. An atmosphere rich in nitrogen provides a stable foundation for more complex chemistry. It creates pressure. It distributes heat. It protects the surface. Oxygen is the real puzzle. Free oxygen is highly reactive. It binds with rocks, metals, and organic compounds. It doesn't persist in an atmosphere without a constant source to replenish it. On Earth, that source is life. Photosynthetic organisms have been pumping oxygen into our atmosphere for billions of years. Without them, Earth's oxygen would disappear within a few million years, locked away in oxidized minerals. So where is LHS 1140b getting its oxygen? Water molecules can be split by ultraviolet radiation in a process called photodissociation. The hydrogen escapes to space while the heaviest oxygen remains. This could explain some atmospheric oxygen, but probably not large amounts. Not enough to create the signals we're detecting. Unless something else is happening. Unless there's a process we don't fully understand generating oxygen at rates far higher than our models predict. Or unless something is producing it. The distance between us and LHS 1140b seems small on cosmic scales. 40 light years. A brief hop compared to the billions of light years we can observe. But it represents an impossible gulf for current technology. The fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour. At that velocity, it would take roughly 65,000 years to reach LHS 1140b. We can't send probes. We can't collect samples. We can only observe from afar, gathering photons that left that distant world decades ago and piecing together the story they tell. Those photons are about to tell us something unprecedented. The James Webb Space Telescope changed everything we thought we knew about looking for life beyond Earth. Before Webb, we were essentially guessing. Telescopes like Hubble can detect exoplanets and measure their basic properties, but atmospheric analysis was crude at best. We could make broad statements about whether a planet might have an atmosphere, but the details, the chemistry, the actual composition, remain frustratingly out of reach. Webb operates in infrared wavelengths, which is critical because molecules absorb and emit light at specific frequencies. Each chemical compound has a unique spectral fingerprint. Methane absorbs light differently than carbon dioxide. Water vapor has its own distinct pattern. Oxygen, nitrogen, sulfur compounds, each one leaves unmistakable traces in the spectrum. When starlight passes through a planet's atmosphere during a transit, some wavelengths get absorbed by atmospheric gases. The light that reaches us carries the signature of everything it passed through. Webb's instruments are sensitive enough to detect these tiny variations, measuring changes in brightness of less than 1 part in 10,000. For LHS 1140b, the initial observations were promising but ambiguous. The data suggested an atmosphere, but the signal was weak. Contamination from the star itself, instrumental noise, and the sheer difficulty of the measurement meant scientists couldn't be certain what they were seeing. Then came the follow-up observations. Multiple transits. Different instruments. Longer exposure times. And the picture began to crystallize. The atmosphere is there. No questions. Thicker than Venus, less dense than Jupiter, somewhere in between. The pressure at the surface could be several times Earth's atmospheric pressure, but not so extreme that chemistry becomes impossible. Nitrogen dominates. That much is clear from the spectral lines. A nitrogen-rich atmosphere is exactly what you'd expect on a world that formed with substantial volatile content and managed to hold on to it. Nitrogen doesn't easily escape because it's relatively heavy and doesn't react readily with other compounds. But the oxygen signal persists across multiple observations. Not overwhelming amounts, but enough to be detected consistently. Enough to demand an explanation. There are 3 possibilities, each with profound implications. First, the oxygen could be abiotic, produced by photodissociation of water vapor in the upper atmosphere. High-energy ultraviolet photons from the star break apart water molecules. Hydrogen, being light, escapes to space. Oxygen accumulates. This process happens on Earth too, but at rates far too slow to maintain significant atmospheric oxygen without biological replenishment. For this to explain LHS 1140b's oxygen, the process would need to be drastically more efficient than our models suggest. Perhaps the star's ultraviolet output is higher than expected. Perhaps the planet's magnetic field is weaker, allowing more atmospheric loss and exposing more water vapor to radiation. Perhaps there's a feedback mechanism amplifying the effect. The math is tricky. You need enough water vapor reaching the upper atmosphere, enough UV radiation to split it, but not so much that you lose all your water to space over geological timescales. The balance is delicate. Second possibility, geological processes. Certain types of volcanic activity can release oxygen. Photosynthesis in the crust, driven by radioactive decay rather than sunlight, could theoretically produce oxygen. These mechanisms are speculative but not impossible. Earth's early atmosphere contained almost no free oxygen until photosynthetic organisms evolved. But there were brief periods, recorded in ancient rock formations, where oxygen levels spiked before collapsing back down. These events remain poorly understood. Some geochemists argue they represent transient geological processes that can generate oxygen without life. Scaling those processes up to explain persistent atmospheric oxygen on LHS 1140b requires assumptions that make many scientists uncomfortable. It's not that it can't happen, it's that we have no examples of it happening at the required scale. Which brings us to the third possibility, the one nobody wants to say out loud without extraordinary evidence: biology. Life is remarkably good at producing oxygen. Cyanobacteria figured out oxygenic photosynthesis roughly 2.4 billion years ago on Earth, and the atmosphere has never been the same since. The process is so efficient, so energetically favorable, that it's hard to imagine advanced life evolving without eventually discovering it. If LHS 1140b hosts life, and if that life has developed photosynthesis, oxygen would be the inevitable result. Not immediately. The first photosynthetic organisms on Earth took hundreds of millions of years to oxygenate the atmosphere, but eventually. Given enough time, biology turns planets into oxygen factories. The problem with the biological hypothesis isn't that it's impossible. It's that it's the most extraordinary claim imaginable, and extraordinary claims demand extraordinary evidence. We need more than just detecting oxygen. We need to rule out every abiotic explanation. We need to find additional biosignatures, gases or combinations of gases that can't be explained by chemistry alone. That's where things get complicated. Methane combined with oxygen is a classic biosignature. Both gases react with each other rapidly. For them to coexist in an atmosphere, something must be constantly replenishing both. On Earth, that something is life. Methane-producing microbes and oxygen-producing plants maintain the balance. Early analyses of LHS 1140b showed possible hints of methane, but the signal was weak. Too weak to be certain. Too weak to publish as a detection. Scientists are being extremely careful here because the stakes are so high. Claiming the discovery of life based on ambiguous data would be career-ending if proven wrong. The scientific community demands multiple independent confirmations, rigorous statistical analysis, and exhaustive consideration of alternative explanations before accepting such a claim. So what we have is a planet with confirmed water, probable nitrogen, likely oxygen, and possible methane. Each observation brings us closer to certainty but never quite crosses the threshold into definitive proof. Meanwhile, theoretical models are being revised in real time. Planetary scientists are running simulations trying to reproduce LHS 1140b's atmospheric composition through purely abiotic means. Some succeeded partially. None match all the observations perfectly. Astrobiologists are working the other direction, asking what a living world around a red dwarf star would actually look like. What metabolic pathways would evolve? What gases would dominate? How would the biosphere respond to tidal locking? The answers are speculative but constrained by physics and chemistry. Life requires energy, it requires liquid water, it requires raw materials. Given those constraints, certain outcomes become more probable than others. One fascinating aspect of LHS 1140b is its potential habitability despite the tidal locking. On a completely tidally locked world with no atmosphere, the day side would be scorching while the night side froze solid. But with a thick atmosphere, heat transport changes everything. Atmospheric circulation would be intense. Superrotating winds could redistribute thermal energy from the day side to the night side, moderating temperature extremes across the planet. Computer models suggest that with sufficient atmospheric pressure, even the night side could maintain temperatures above freezing. The twilight zone, that permanent ring between eternal day and endless night, becomes the most interesting real estate in the system. Here, the sun hangs forever at the horizon. Temperatures are moderate. Light is dim but constant. If life exists on LHS 1140b, this is where it would thrive. Imagine standing in that twilight zone. The sun never moves, locked in its position just above the horizon. The sky is a gradient from bright to dark, never fully day, never completely night. The wind is constant, driven by the temperature differential between the two hemispheres. The landscape might be ice in one direction, ocean in the other, with rivers flowing eternally toward the night side where water freezes and returns as snow blown back by the wind. This isn't science fiction. This is the most likely scenario based on our current understanding of how atmospheres behave on tidally locked worlds. And somewhere in this alien landscape, if the oxygen signal is biological, something lives. Something has survived for potentially billions of years, adapted to conditions utterly unlike anything on Earth, evolving under a dim red sun that never sets. The next set of observations is already scheduled. Webb will observe LHS 1140b multiple times over the next 2 years, building up signal strength, searching for those captured methane signatures, measuring the ratios of different atmospheric components with increasing precision. Each data point narrows the possibilities. Each observation brings us closer to an answer that will fundamentally change how we see ourselves in the cosmos. Because here's what nobody wants to acknowledge too loudly: we're running out of abiotic explanations. The combination of water, oxygen, and possible methane in those specific ratios doesn't match any purely geological model perfectly. The numbers keep pointing in one direction. And if that direction is confirmed, if the evidence becomes undeniable, we'll have discovered something that transforms everything. Not just astrobiology, not just planetary science, but philosophy, religion, culture, our fundamental understanding of life's place in the universe. But there's a problem nobody's talking about yet. one that might be even more profound than the question of whether life exists on LHS 1140b. The problem is distance and time. LHS 1140b is 48 light-years away. Every observation we make shows us the planet as it was 48 years ago. The light carrying those atmospheric signatures left that world in 1977. If something is alive there now, we're not seeing it now. We're seeing its ancestors. This creates a strange philosophical tension. We could confirm biological activity on LHS 1140b tomorrow, prove beyond doubt that life exists somewhere else, and yet we'd be detecting life that existed when Voyager 1 launched. The organisms producing that oxygen, if they exist, might have already evolved into something completely different. They might be extinct. The entire biosphere could have collapsed decades ago and we wouldn't know for another decade. Distance doesn't just delay information. It separates causality. Nothing we do can affect LHS 1140b. Nothing happening there can affect us. The light-speed barrier makes this a purely analytical relationship, one way and fundamentally disconnected. But here's what makes it worse. Even if we confirm life, even if every measurement points to biology, we'll never visit. Not with current technology. Not with any foreseeable technology. 48 light-years might as well be 48 million. The fastest probe humanity has ever built, Parker Solar Probe, travels at about 430,000 miles per hour relative to the Sun at its closest approach. Sounds impressive until you calculate how long it would take to reach LHS 1140. At that speed, covering 48 light-years would take roughly 70,000 years. And that's assuming we could maintain that velocity, which we can't. Parker achieves that speed through gravitational assists near the Sun. In interstellar space, it will slow dramatically. Even with theoretical fusion propulsion, the kind we might develop in the next century, we're looking at journeys measured in thousands of years. Generation ships. Sleeper ships. Concepts that blur the line between mission and migration. You don't visit LHS 1140b. You abandon Earth and hope your descendants arrive. This is the cruel joke of astronomical discovery. We can detect water on distant worlds. We can measure atmospheric composition across dozens of light-years. We can identify chemical signatures that might indicate life. But we can't touch it. Can't sample it. Can't send back anything more than electromagnetic radiation and wait decades for a response. The James Webb Space Telescope costs $10 billion and represents the absolute cutting edge of observational astronomy. It can tell us what gases exist in the atmosphere of LHS 1140b with remarkable precision. But it can't tell us if those gases are being produced by microbes or by chemical reactions we haven't thought of yet. It can't distinguish between a thriving biosphere and a dead world with interesting geography. Not with certainty. That distinction requires context. It requires understanding the planet's history, its geological activity, its weather patterns, the distribution of those gases across the atmosphere. It requires decades of continuous observation, building up data sets, watching for seasonal variations, tracking changes over time. And even then, even with perfect data, we might never be absolutely sure. This is where the optimists and pessimists diverge sharply. The optimists point to the oxygen levels, the possibility of methane, the presence of liquid water. They argue that the combination is too specific, too unlikely to arise from non-biological processes. They're probably right. Statistically, biologically produced oxygen is the most parsimonious explanation. The pessimists counter with unknowns. We've studied exactly one planet with life in detail. Sample size of 1. We don't know what other chemical pathways might produce similar signatures under conditions that don't exist in our solar system. We don't know what exotic geology might arise on a world orbiting a red dwarf with tidal locking and extreme temperature differentials. We're extrapolating from Earth-based knowledge to environments radically unlike Earth. Both sides have valid points. Both sides are constrained by the same fundamental problem: we can't go there. So what's the alternative? We wait. We observe. We refine our measurements. We build better models. And we accept that the answer might remain frustratingly ambiguous for generations. Unless we detect something unmistakable. Something that couldn't possibly be geological. The holy grail of astrobiology would be detecting something like chlorophyll, or its alien equivalent. A pigment specifically evolved to capture light energy. On Earth, chlorophyll has a distinctive spectral signature, a sharp absorption feature in the red part of the spectrum. It's called the red edge, and it's so characteristic of photosynthetic life that some scientists have proposed looking for it directly in exoplanet observations. The problem is sensitivity. Detecting something like a vegetation signature requires observing the planet's surface directly, not just its atmosphere. It requires distinguishing between light reflected from clouds, oceans, ice, and land masses. It requires resolution that current telescopes simply don't have. But future telescopes might. The proposed Habitable Worlds Observatory, still in early design phases, will be specifically optimized for characterizing Earth-like planets. It would have the resolution, the sensitivity, and the wavelength coverage to potentially detect biosignatures at the surface level. If funded and built, it might launch in the 2040s. That's 20 years away. Minimum. And that's if everything goes perfectly, which it never does. In the meantime, we're leaving with atmospheric chemistry. Gases. Ratios. Spectral lines. The most indirect evidence possible. It's like trying to determine if a house is occupied by analyzing the smoke coming from its chimney. You can make educated guesses, but you can't see inside. Yet this is the frontier. This is as close as we can currently get to answer the oldest question humanity has ever asked: are we alone? LHS 1140b sits at the center of that question right now. Not because it's the only candidate. Not because it's the most Earth-like exoplanet we've found. But because it's the one where the evidence is accumulating fastest, where the atmospheric signals are strongest, where the physics and chemistry align in ways that keep pointing toward biology. The scientific community is being cautious. appropriately so. Nobody wants to be the person who announces alien life only to have it debunked 6 months later. The bar for claim detection is extraordinarily high. It should be. But privately, in conversations that don't make it into official papers, researchers are getting excited. The oxygen levels are too high. The possibility of methane is too tantalizing. The liquid water is too perfect. It's starting to feel less like a question of if and more like a question of when the confirmation comes. And that's where things get complicated in ways most people haven't considered. Because discovering life on LHS 1140b, proving it exists, changes the equation for every other exoplanet we've found. We've cataloged over 5,000 confirmed exoplanets. Hundreds of those are potentially habitable. Most haven't been studied in detail because telescope time is limited and atmospheric characterization is expensive. We've prioritized the closest, the most promising, the ones that transit their stars in ways that make observation easier. But if LHS 1140b has life, that changes the prior probability for every other planet on the list. It transforms the search from looking for a possible unique phenomenon to looking for a potentially common one. It justifies spending resources on worlds we might have otherwise ignored. It turns astrobiology from a speculative field into an empirical science. The implications cascade outward. If life arose independently on LHS 1140b, then the galaxy might be filled with biospheres. Not intelligent life necessarily. Not civilizations. But microbes. Ecosystems. Planets where chemistry crossed the line into biology and never looked back. This is the part that keeps cosmologists awake at night. Because if life is common, if it arises whenever conditions are roughly suitable, then the Fermi paradox gets sharper. Where is everyone? If biology is easy, why aren't the stars filled with radio signals and megastructures? Maybe intelligence is rare. Maybe the jump from simple life to complex multicellular organisms is the hard step. On Earth, it took 3 billion years for life to evolve beyond single cells. 3 billion years of bacteria and archaea before the Cambrian explosion. Maybe that's typical. Maybe the galaxy is full of microbial worlds and empty of anything more complex. Or maybe we're looking at the answer right now. Maybe tidal locking is the problem. LHS 1140b, if it has life, is locked in place. Extreme environments on both hemispheres. A narrow habitable zone in the twilight ring. Perhaps that's stable enough for microbes but too constraining for complex multicellular organisms to evolve. Perhaps intelligence requires the kind of dynamic environment that only comes with planetary rotation and seasonal variation. These are the questions that multiply faster than answers. Each observation spawns 10 new uncertainties. Each data point opens 5 new research directions. This is what makes the science both frustrating and exhilarating. We're not just discovering a planet. We're discovering how much we don't know about how life works at a fundamental level. The timeline for answering these questions is measured in years, not months. JWST observations are scheduled in competitive cycles. Each target competes with dozens of others for telescope time. LHS 1140b has secured multiple observation windows, but atmospheric characterization isn't something you do in a single session. You need repeated observations across different orbital phases, multiple transits, different wavelengths, cross-referencing data sets to rule out instrumental artifacts or stellar contamination. The planet transits its star every 25 days. Each transit gives a few hours of usable data. Building a complete atmospheric profile requires dozens of these observations. Factor in scheduling constraints, data processing time, peer review, and the cautious pace of scientific publication, and you're looking at a multi-year process before any definitive statements get made. This is the unglamorous reality of exoplanet science. Discovery happens in press releases. Confirmation happens in spreadsheets and error bars and statistical significance tests that most people will find unbearably tedious. The public wants answers now. Science delivers answers eventually, with caveats attached. But here's what makes this particular waiting game different. We're not waiting to see if the planet exists. We're not waiting to confirm it's in the habitable zone. We're not even waiting to verify it has an atmosphere. All of that is already established. We're waiting to find out if the atmosphere contains the specific molecular signatures that would indicate biological activity. The difference is profound. For the first time in human history, we have the technology to answer the question directly. Not through speculation or statistical probability. Through observation. Through chemistry. Through the specific absorption lines in a spectrum that can only be explained by life continuously pumping oxygen into an atmosphere faster than geography can remove it. The equipment exists. The target is identified. Now it's just a matter of data accumulation. That's a fundamentally different situation than we've ever been in before. Consider what that means psychologically. Every astronomer working on this project knows they might be the person who confirms extraterrestrial life. Not discovers it, because the planet was already found. But confirms it. Proves it. Puts their names on the paper that changes everything. That's extraordinary pressure. It's also extraordinary motivation. The data gets checked and rechecked. Models get refined. Alternative explanations get explored exhaustively. Because the standard for this particular claim isn't just peer review. It's history. It's the kind of announcement that gets carved into the permanent record of human knowledge. Nobody wants to be wrong about this. And yet, the preliminary data keeps pointing in the same direction. The oxygen levels remain stubbornly high. The temperature models keep suggesting liquid water oceans. The atmospheric chemistry continues to look like something actively maintained rather than something in equilibrium. Each new observation narrows the uncertainty without eliminating the possibility. This is what scientific tension looks like. Not dramatic. Not explosive. just a slowly tightening vise of evidence that makes certain conclusions harder and harder to avoid. Meanwhile, other research teams are looking at the problem from completely different angles. Some are focusing on polarimetry, studying how light reflects off the planet's atmosphere and surface. Different molecules create different polarization signatures. Life, particularly photosynthetic life, creates distinctive patterns. Chlorophyll has a specific reflectance spectrum. So do to other biological pigments. If LHS 1140b has oceans with photosynthetic organisms, we might be able to detect that directly. Others are modeling the planet's climate in unprecedented detail. Building simulations that account for tidal locking, atmospheric circulation, ocean currents, heat transport from day side to night side. These models help predict where life would most likely exist if it's there. They also help identify what kinds of biosignatures we should be looking for and in what concentrations. There's even work being done on the planet's formation history. How did it end up with so much water? Did it form in place or migrate inward from a colder region of the system? The answer matters because it affects the planet's bulk composition, which affects its geology, which affects the availability of nutrients and minerals that life might need. All of these research threads are running in parallel. Each one contributes a piece to the larger puzzle. And increasingly, the pieces are fitting together in ways that suggest something remarkable. But let's address the elephant in the room. What if we're wrong? What if all this oxygen has some exotic geological source we haven't considered? What if the atmospheric chemistry is being driven by processes that have nothing to do with biology? It's possible. Unlikely, but possible. Science has been surprised before. Venus has sulfuric acid chlorides that look nothing like what early models predicted. Titan has methane lakes that create a hydrological cycle without any water. The universe is creative in ways we continuously underestimate. So the researchers are doing what scientists do. They're trying to break their own hypothesis. Actively looking for non-biological explanations that could produce the observations. Testing edge cases. Exploring scenarios that seem far-fetched but aren't technically impossible. This is the opposite of confirmation bias. This is structured skepticism applied with rigor. And so far, the non-biological explanations keep failing. They require special circumstances that are geologically unstable or affectedly implausible. They predict other atmospheric components that we're not seeing. They create contradictions with the temperature data or the planet's mass or the star's radiation spectrum. One by one, the alternative explanations are being ruled out. Not because anyone wants them to fail, but because the data doesn't support them. That's how science is supposed to work. You don't get to choose what the universe tells you. You just get to choose how carefully you listen. There's another consideration that doesn't get discussed much in the technical papers but matters enormously. The political and cultural implications of confirming life on LHS 1140b. This isn't just an academic question. It's a civilizational milestone. The kind of event that gets taught in history classes centuries from now. different groups will interpret the discovery in wildly different ways. Some will see it as validation of religious beliefs about creation's abundance. Others will see it as confirmation that life is a chemical inevitability. Some will use it to argue for increased space exploration funding. Others will use it to argue we should focus on protecting Earth's biosphere since life might be more fragile than we thought. These debates are already happening in anticipation. The actual confirmation will intensify them exponentially, which means the scientists making the announcement need to be extremely careful about how they communicate their findings. Not just the what, but the how certain and the what it means. This is partly why the process is so slow. It's not just about getting the science right. It's about getting the communication right. About making sure the claims are bulletproof before they enter the public discourse, where they'll be amplified, distorted, and weaponized in ways the researchers can't control. The scientists working on this are acutely aware they're not just publishing a paper. They're potentially rewriting humanity's understanding of its place in the universe. That's not hyperbole. That's the literal stakes. And here's what makes it even more complex. If LHS 1140b had life, we'll never be able to study it directly. Not in our lifetimes. Probably not in our grandsons' lifetimes. The planet is 40 light-years away. Even traveling at 1/10 the speed of light, which is far beyond our current capabilities, it will take 400 years to get there. We're not sending probes. We're not collecting samples. We're not doing experiments. Everything we learn will come from light. From spectroscopy. From watching how the planet's atmosphere absorbs and reflects radiation from its stars. That's it. That's the entire toolkit. Which means the discovery, if it comes, will be simultaneously profound and surprising. We'll know life exists beyond Earth. We won't be able to study it in detail. We'll have confirmation of biology's existence. We won't know what it looks like, how it evolved, whether it's cellular, whether it has DNA. None of that. We'll be limited to atmospheric chemistry and mathematical models. We'll infer biological processes from oxygen concentrations and methane ratios. We'll guess at evolutionary history from planetary conditions and stellar radiation levels. But we won't know. Not the way we know things through direct observation and experimentation. This is the fundamental limitation of exoplanet science. We find worlds. We characterize their basic properties. But we can't touch them. Can't visit them. Can't run experiments. We're astronomers, not biologists. We work with light and mathematics, not samples and laboratories. For some researchers, this limitation is maddening. For others, it's clarifying. It forces extreme rigor in interpretation. It demands that conclusions be drawn only from what can be definitively observed. It eliminates the possibility of contamination or experimental error. The data is what it is. The universe doesn't lie. And that's where we are right now. Waiting. watching, analyzing data that's already been collected while new observations continue to accumulate. The James Webb Space Telescope has LHS 1140b on its observation schedule. So do ground-based telescopes around the world. Every transit adds more data points. Every spectrum adds more detail. The picture is getting sharper. Slowly. But it's getting sharper. What happens if the answer is yes? If the data conclusively shows biosignatures, the scientific community will do what it always does. It will scrutinize the findings with brutal intensity. Other teams will reanalyze the data using different methods. They'll look for alternative explanations. They'll challenge assumptions. They'll demand additional observations to rule out false positives. This isn't skeptical for its own sake. It's the scientific method operates exactly as designed. Claims require evidence. Extraordinary claims require extraordinary evidence. And nothing is more extraordinary than confirming life on another world. The process could take years, maybe decades. Not because scientists are being stubborn, but because the stakes demand absolute certainty. You don't announce the discovery of extraterrestrial life based on a single spectral line or a tentative detection. You need multiple independent confirmations. You need to rule out every possible non-biological explanation. You need consensus across the scientific community. That takes time. Meanwhile, public interest will be intense. Every paper published about LHS 1140b will be covered by media outlets looking for the next big headline. Every conference presentation will be dissected. Every researcher involved will face questions they can't fully answer yet. The gap between what scientists know and what the public wants to know will be enormous. And that gap will be filled with speculation, premature conclusions, and misinterpretations. It's inevitable. The challenge will be maintaining scientific integrity while promoting genuine public interest. Not shutting down curiosity, but channeling it toward understanding the process. Helping people grasp why certainty takes time. Why caution isn't the same as doubt. Why the absence of a definitive answer right now doesn't mean the question isn't being pursued with extraordinary rigor. Here's something most people don't realize about exoplanet research. The limiting factor isn't usually the technology. It's time. Specific, observation time on the world's most powerful telescopes. These instruments are in constant demand. Thousands of researchers compete for access. Observation schedules are planned years in advance. Getting enough time to fully characterize a planet like LHS 1140b requires proposals, peer review, committee allocations, and coordination across multiple facilities. It's a known process overlaid on a scientific one. Which means even when researchers know exactly what observations they need, getting those observations observed can take years. This isn't ineffective. It's the reality of limited resources and unlimited questions. The scientists studying LHS 1140b aren't just waiting for data. They're actively modeling what that data should look like under different scenarios. If the planet had life, what would the spectrum show? If it doesn't, what instead? If there's an ocean but no biology, how would that appear? If there's a thick atmosphere with no surface water, what would the signature be? They're building frameworks for interpretation before the data arrives. This preparatory work is crucial. When you're looking at light that's traveled 40 years through space, you need to know what you're looking for. You need models that account for stellar contamination, atmospheric chemistry, planetary geology, and potential biological processes. You need to distinguish between signals that indicate life and signals that merely look like they might. The difference between those two things is everything. And here's where it gets philosophically interesting. What counts as life? We have a working definition based on Earth biology. Metabolism, reproduction, response to environment, evolution through natural selection. But what if alien life doesn't fit that definition? What if it's organized differently, uses different chemistry, operates on principles we haven't imagined? The search for biosignatures assumes life elsewhere will be biochemically similar to life here. That's a reasonable assumption based on the universality of chemistry. Carbon bonds the same way everywhere. Water has the same properties throughout the universe. Thermodynamics doesn't change based on location. So biology elsewhere should follow similar patterns? Probably. But what if it doesn't? What if we're looking for oxygen and methane while the actual biosignatures are compounds we haven't considered? This is the epistemological challenge at the heart of astrobiology. You can only search for what you can imagine. You can only detect what your instruments are designed to find. If life is radically different from Earth life, we might look right at it and not recognize it. This keeps some researchers up at night. The flip side is equally important. What if we find something ambiguous? A chemical signature that could be biological but could also be geological. Methane, for instance, can be produced by life. It can also be produced by volcanic activity, serpentinization, or atmospheric chemistry. Finding methane on LHS 1140b wouldn't be proof of life. It would be interesting. It will warrant further investigation. But it wouldn't be conclusive. The real breakthrough will be finding multiple biosignatures in combination. Oxygen and methane together, for example, which on Earth only coexist because biology continuously produces both. Or finding gases in ratios that can't be explained by non-biological chemistry. Or detecting seasonal variations that suggest biological cycles. The more lines of evidence, the stronger the case. But even then, certainty is elusive. There's a concept in science called the extraordinary claim threshold. It means the strength of evidence required scales with the unusualness of the claim. If you claim to have found a new type of bacteria in a lake, you need decent evidence. If you claim to have found a bacterium that violates the laws of thermodynamics, you need extraordinary evidence. And if you claim to have found life on another planet, You need evidence so overwhelming that every alternative explanation has been scientifically eliminated. We're not there yet with LHS 1140b. We might never get there. Not because the planet doesn't have life, but because proving it from 40 light years away might simply be beyond what's possible with current technology. That's the surprising reality. The universe doesn't owe us easy answers. But here's what we do have. We have a planet in the habitable zone of a quiet star. We have evidence suggesting liquid water could exist on its surface. We have the technological capability to analyze its atmosphere in detail. And we have teams of scientists dedicating their careers to extracting every possible insight from the available data. That's not nothing. That's actually remarkable. 50 years ago, we didn't know if planets existed around other stars. Now we're debating the atmospheric chemistry of specific worlds and whether those chemistries indicate biology. The progress is staggering. And regardless of what we find on LHS 1140b specifically, the search continues. There are other candidates. Other planets being studied. Other telescopes are being built. The sample size is growing. Every negative result narrows the search parameters. Every ambiguous result refines our understanding of what biosignatures actually look like. Every confirmed detection of water or oxygen or methane adds to our database of planetary atmospheres. We're building a map of possibilities, charting the landscape of what planets can be. And somewhere in that landscape, life exists. Probably. The question is whether we'll recognize it when we find it. The James Webb Space Telescope will operate for another decade at least, possibly two. Ground-based telescopes continue to improve. New missions are being planned. The European Extremely Large Telescope will come online in the next few years with unprecedented light-gathering capacity. The field is hurriedly. The tools are getting better. The questions are getting sharper. And the answers, when they come, will reshape everything. Not just our understanding of biology or planetary science, but our understanding of ourselves, our place, our significance, whether we're alone or part of something greatly larger. That's what makes LHS 1140b more than just another exoplanet. It's a test case, a laboratory for working out how we'll approach these questions as the technology improves. How we'll communicate uncertainty. How we'll handle ambiguous results. How we'll maintain scientific rigor while expanding the profound implications of what we might find. Every observation of this planet is practice for the moment when we finally have enough data to make a definitive claim. And when that moment comes, assuming it does, the world will be watching. Not just scientists. Everyone. Because the discovery of life beyond Earth isn't a scientific achievement. It's a civilizational milestone. The kind that gets reminded for as long as humans exist to remember anything. So what happens next with LHS 1140b? The honest answer is we wait. We accumulate more observation time. We refine our models. We compare this planet to others in our growing catalog of studied worlds. We look for patterns that might reveal something deeper than any single data point can show. The next round of observations is already planned. Different instruments, different wavelengths, longer exposure times to faint catcher signals. Each observation adds pixels to the image we're building. Not a literal image, the planet is too far away for that. But a conceptual one. A model of what this world might actually be like. And here's something most people don't realize about this process. Every observation doesn't just tell us about the planet. It tells us about the limits of our instruments. When we point James Webb at LHS 1140b and measure its atmosphere, we're simultaneously testing how well our equipment can distinguish real signals from noise. We're calibrating. Learn what our tools can and cannot do. That matters because LHS 1140b isn't the end goal. It's one target among many. If we can perfect our techniques here, we can apply them elsewhere. To planets around different stars, at different distances, with different atmospheric compositions. We're building a playbook. Some researchers are already talking about what comes after James Webb. Telescopes that don't exist yet but are being designed right now. Instruments with 10 times the sensitivity, 100 times the resolution. Capabilities that would make questions that seem impossible today routine in 30 years. But that's the long game. Right now, in the immediate term, the focus is on extracting every bit of information possible from existing data. And that means collaboration. Not just between observatories or institutions. Between entire scientific disciplines. Atmospheric chemists work with planetary geologists. Biologists consult with astronomers. Computer scientists build models that physicists test against observational constraints. The search for life beyond Earth isn't happening in a single lab. It's a distributed effort involving thousands of people across dozens of countries. And they're not just looking at LHS 1140b. They're looking at hundreds of exoplanets. Building databases. Running comparative analyses. Trying to understand which features are common and which are rare. Because context matters. If we find oxygen in the atmosphere of LHS 1140b, that's interesting. If we find oxygen in the atmospheres of 20 similar planets, that changes the interpretation. It might suggest oxygen is more common than we thought. That it can arise through non-biological processes we haven't fully understood. Or it might strengthen the case that life is widespread. We don't know yet. The sample size is still too small. But here's what keeps researchers going despite the uncertainty. The possibility. The chance that we're living through a historic moment. That somewhere in the data we're collecting right now is the signature of something alive. Something that evolved independently of Earth. That would be profound in ways that are hard to articulate. It would mean life isn't a fluke. It's not a one-time accident that happened on our planet and nowhere else. It's a natural consequence of chemistry and physics under the right conditions. And if it happened twice in one small corner of one galaxy, it's probably happened billions of times across the universe. That realization would reframe everything. Not immediately. Not in some dramatic overnight shift. But gradually. Over years and decades as the implications sank in. As we begin to understand what it means for biology. For evolution. For the future of our own species. Because if life exists elsewhere, even simple microbial life, it tells us something about our own trajectory. It suggests that the emergence of life isn't the hard part. The hard part is everything that comes after. Multicellular organization. Intelligence. Technology. Civilization. And if we're the only intelligent life in our local neighborhood of the galaxy, that raises its own questions. Why us? Why here? Why now? What conditions allow intelligence to evolve on Earth but apparently nowhere else within dozens of light years? These aren't just philosophical questions. They're scientific ones. They have implications for how we think about the future. About whether intelligence is common or rare. About whether technological civilizations tend to survive or destroy themselves. About whether we should expect to find anyone out there when we look. LHS 1140b can't answer all of that. But it can give us one data point. One example of what happens when you take a rocky planet, put it in the habitable zone, give it billions of years, and see what emerges. Right now, we're in the ambiguous middle. We have enough data to be interested but not enough to be certain. We have tantalizing hints but no smoking gun. We have possibilities but no proof. That's frustrating. But it's also appropriate. This is how science works. Slowly. Carefully. Building understanding piece by piece. Never jump to conclusions. Always demanding more evidence. And the evidence will come. Maybe not next year. Maybe not in 5 years. But eventually, as our instruments improve, as our observation time increases, as our theoretical models become more sophisticated, the picture will sharpen. We might find that LHS 1140b is just a wet rock with interesting chemistry. No life. Just water and minerals and atmospheric dynamics that happen to produce patterns we initially misinterpreted. That's possible. Maybe even likely. Or we might find something that can't be explained without invoking biology. Some combination of gases that only make sense if something is actively producing them. Some seasonal variation that tracks with what we'd expect from photosynthetic organisms. Some chemical signature that screams life even from 40 light years away. We don't know which outcome we're heading toward. But we'll find out. One observation at a time. One analysis at a time. One peer-reviewed paper at a time. And when we do, When we finally have enough data to make a confident statement about this planet, it won't be the end of the story. It'll be the beginning of a new chapter. Because then we'll know what to look for. What biosignatures actually look like on a real exoplanet rather than in theoretical models. How to distinguish them from false positives. What kinds of stars and planets are most likely to host life. That knowledge is the foundation for everything that comes next. For the next generation of telescopes. For the next 1,000 exoplanets we study. For the long-term project of mapping life in the universe. LHS 1140b is one planet. But it represents something larger. It's a test case. A laboratory for working out how we'll approach these questions as technology improves. How we'll convey uncertainty and ambiguity that comes with trying to detect life from impossibly far away. So far, we are passing that test. We are asking the right questions. Building the right instruments. Conducting the right observations. Analyze the data with appropriate skepticism and rigor. But the final exam is still ahead. And we won't know if we've passed until the results are in. What's remarkable is that we are even in a position to take that exam. For most of human history, questions about life on other worlds have been purely philosophical. There was no way to investigate them. No data to collect. No experiments to run. You could speculate. You could imagine. But you couldn't know. Now we can know. Not easily. Not quickly. Not with certainty on the first try. But we have tools. We have methods. We have the capability to point our instruments at a planet 40 light years away and ask if anything is alive there. That's astonishing. It's a capability our ancestors couldn't have dreamed of. And it's a responsibility. Because if life is out there, if LHS 1140b or some other world harbors biology, we have a duty to find it. To study it. To understand it. Not to exploit it or contaminate it. But to learn from it. Every living thing on Earth shares a common ancestor. We are all part of one evolutionary tree. One experiment in what life can become. If we find life elsewhere, even simple life, we gain a second data point. A second tree. A second experiment. And two experiments tell you vastly more than one ever could. They reveal what is universal and what is contingent. What is inevitable and what is accidental. What happens every time and what only happened here. That's the promise of LHS 1140b. Not certainty. Not immediate answers. But the possibility of a second data point. A comparison. A way to begin understanding life not just as it exists on Earth, but as a general phenomenon in the universe. That planet sits out there, 40 light years away, orbiting its red dwarf star. Its atmosphere, if it has one, is interacting with starlight. Chemical reactions are occurring. and some of those processes may be biological. We are watching, measuring, analyzing, building our understanding one observation at a time. The answer, whatever it turns out to be, is already there. We just haven't finished gathering enough data to see it clearly yet. But we will. That's not optimism. That's just how this works. You point your instruments at the target. You gather photons. You process the data. You build your models. And finally, the picture resolves. Whether that picture shows life or just chemistry, it will be real. It will be based on evidence. And it will move us one step closer to understanding our place in a universe that's vastly larger and stranger than we can fully comprehend. The fundamental question isn't whether LHS 1140b has life. The question is whether we're asking it correctly. Are our definitions of biosignatures broad enough? Are our instruments sensitive enough? Do our theories account for the full range of possibilities that chemistry and physics allow? Because this is something nobody wants to admit out loud. We might be looking at life right now without realizing it. The oxygen signal might be biological. The atmospheric composition might be exactly what you expect from a thriving biosphere. And we might spend decades debating whether it's conclusive enough while the answer sits there in the data, obvious in retrospect. Or we might be seeing patterns that aren't real. Interpreting noise, or we might be seeing patterns that aren't real. Interpreting noise as signals. Finding meaning in atmospheric chemistry that's purely geological. Building elaborate theories about alien biology when the real explanation is mundane and non-living. Both scenarios are uncomfortable. Both require humility regarding our limitations. Both demand that we keep observing, keep analyzing, keep refining our understanding without jumping to conclusions in any direction. The price is too high for anything else. If we claim life exists and we are wrong, we damage the credibility of an entire field. If we dismiss evidence that is truly biological because we are too cautious, we miss one of the most important discoveries in human history. Threading that needle requires precision. It requires acknowledging uncertainty while making progress. It requires being comfortable with ambiguity until it takes to resolve. And that can take years, decades, even. The universe operates on a timescale that disregards human curiosity or impatience. We have answers when we have enough data, not before. What makes LHS 1140b historically significant isn't what we found. It's what we're capable of finding. 50 years ago, this dialogue wouldn't have been possible. The technology didn't exist. The methods weren't developed. The theoretical framework wasn't mature enough. Now we can point instruments at a world 40 light-years away and measure its atmospheric chemistry with enough precision to debate whether oxygen levels indicate biology. That capability emerged in a single lifetime. Its impact is yet not fully registered. We are living through a transitional phase from wondering whether life exists elsewhere to actually testing it. Not through speculation, through observation. Through data. Through the slow, laborious work of extracting information from photons that have traveled decades to reach us. And whatever LHS 1140b turns out to be, the search doesn't stop there. There are thousands more planets, more stars, more potential biospheres waiting to be characterized. Sample size will grow. Technology will improve. The questions will become sharper. Eventually, we will find something definitive. Maybe on this planet. Maybe on another. But somewhere in our ever-growing catalog of exoplanets, either there is life or there isn't. And we are getting closer to knowing which one. It's not a prophecy. It's just the trajectory we're on. Every telescope built. Every observation scheduled. Every model refined. Every paper published. They are all steps toward an answer that will fundamentally change how we understand ourselves. Because we are not separate from this question. We are a part of it. We are an example of what happens when chemistry crosses the line to become biology and continues to evolve. Whether we are the only example or one of countless others will determine our place in a universe indifferent to our existence but shaped by the same laws of physics everywhere. LHS 1140b won't answer that alone. But it is teaching us how to ask the right questions. How to design observations. How to interpret data. How to maintain seriousness while pursuing something that sounds like science fiction but isn't. This is the ultimate boundary. Not the edge of space. Not the boundary of what is physically attainable. But the limit of what we can know from where we stand. And that limit is expanding. Slowly. Methodically. One observation at a time. The planet orbits its star every 25 days. Each transit is another opportunity to gather data. Another opportunity to refine our understanding. Another piece of the puzzle slipping into place. We don't wait for a miracle. We wait for enough evidence to accumulate to make a defendable claim. That's less dramatic but more honest. Science doesn't work through sudden enlightenments. It works through patiently accumulating information until the picture becomes clear enough to see. And when that happens, when we finally know what LHS 1140b really is, the real work begins. Because knowing one planet in detail opens up questions about everything else. About which features are common and which are rare. About which conditions favor life and which hinder it. About whether intelligence is inevitable or whether we are witnessing something that is almost never going to happen. Those questions don't have answers yet. But they will. Finally. As our capabilities expand and our scope grows. As we shift from studying individual planets to studying planetary populations. As we move from asking whether life exists elsewhere to asking where, how often, and under what conditions. That transfer is happening right now. In real time. In data collected by telescopes operating at the absolute limits of what is technically possible. In papers written by researchers who understand that they are not only advancing their field but also contributing to one of the oldest questions humanity has ever posed. The answer, whatever it may be, will not come from a single observation or a single paper. It will rise from the accumulated weight of evidence, from many lines of investigation pointing in the same direction, from the slow, deliberate process of eliminating alternatives until only one explanation remains. That is how we will know. Not through intuition or hope or expectation. Through data. Through chemistry. Through the patient application of the scientific method to a question as profound as any we have ever faced. LHS 1140 be 40 light-years away. That distance will never change. We will never visit. Never collect samples. Never run experiments at that location. Everything we learn will come from light. From spectroscopy. From mathematical models and theoretical frameworks validated through observation. That is both our greatest limitation and our greatest achievement. We have found a way to study worlds we cannot reach, to analyze atmospheres we cannot sample, to search for life we cannot see directly. And we are doing it with enough precision for the results to truly matter.